Hello students, very good afternoon. Welcome to the NEET crash course chemistry session. We have practically have brought exclusively this session or this course for you people because all of you know that NEET exam has been scheduled on 12th of September. So on the grounds of that, we have brought a NEET crash course where we will be covering a chemistry and biology subjects for the next 18 to 20 days, okay, where you will get to see or you get to learn all the concepts and all the types of questions that you needed for you to crack that dream exam of yours. Okay, that is why we have brought this exclusive course for you, a NEET crash course brought by Practically. So let's begin. In today's session, we're gonna start the chapter which is most important from the physical chemistry. Why I'm saying most important? Because this chapter encompasses so many concepts from the other chapter also. And one more thing, there have been so many questions being asked on this particular chapter, and that is why I know it's very difficult to cover this whole chapter in this single session, but I tried my best to bring as much important concept and as much important questions for you to crack that dream exam of yours. Okay, chalo, we're gonna start on that note. So this is Mayur More welcoming you all. Very good afternoon. Okay, let's begin. Chemical and ionic equilibrium. Okay, chalo. So chemical equilibrium. So we already know what chemical equilibrium is, right? It is not just a reverse reaction. It is not a reaction which is just a reversible reaction. It is a reaction where rate of forward reaction and rate of backward reactions are exactly same. That means number of moles of reactant going into the product and number of moles of product coming into the reactant are exactly same. That does not mean reaction is stationary. Okay, chemical equilibrium is always dynamic. You can move it, like you can increase the amount of product, you can increase the amount of reactant also. So if you look at the equation for Kc, okay, suppose if you are having A moles of A reacting with B moles of B to give C moles of C and D moles of D. Okay, now this small a, small b, small c and small d, what are those? Those are called as stoichiometric coefficients. Okay, and a, b, c and d, capital I mean, these are the species which are reacting in that particular reaction. Then how do we write a Kc for this? The Kc is equal to C raised to C D raised to D divided by A raised to A and B raised to B. So basically your Kc, or I would say equilibrium constant, is the ratio of product of products to the product of reactants, with each concentration term raised to its stoichiometric coefficient in the balanced chemical equation. That is what is Kc. Okay, then what is Kp? Kp is applicable to those species which are undergoing reaction in a gaseous medium. That means in when you can apply Kp when all the reactants and all the products are in a gaseous phase. That's when only you can apply the Kp. And what is the relation between Kp and Kc? Kp stands for the pressure, partial pressure of gases, because because when all of them are in a gaseous phase, then the concentration of given species can be found out by partial pressure of that species only. And what is the formula for partial pressure? Partial pressure is the total pressure of that particular species multiplied by its mole fraction. Okay, by considering all of that, we derive the equation Kp is equal to Kc RT raised to delta Ng. Kp is equal to Kc RT raised to delta Ng, where you know what delta Ng is. Delta Ng is the total number of gaseous molecules of product minus total number of gaseous molecules of reactant. So that means if the number of gaseous molecules of product and gaseous molecules of reactants are same, then your delta Ng becomes 0. When delta Ng becomes 0, RT raised to 0. RT raised to 0 means what? Anything raised to 0 is always equal to 1. In that case, when number of moles of gaseous product and number of moles of gaseous reactant are same, in that case, Kp is equal to Kc. In other words, if delta Ng is 0, then Kp is equal to Kc. Okay. Now we don't need to remember this, that we don't need to remember this. You can simply see that in a mathematical terms also. You just need to remember Kp is equal to Kc RT raised to delta Ng. Now there is a derivation for that, but we are appearing for an objective exam, right? So we don't need to remember the derivation. You can just remember the formula. That is what my job is here. I'm bringing out all the necessary formula that is necessary for you to solve the numericals. Okay. So moving ahead. Le-Chatelier's principle. So this Le-Chatelier principle is extremely important in your chemical equilibrium. It is very important because this will dictate the terms. This will dictate the terms based on which you can find out how we can tilt given reaction to the product side. Because why we are performing the reaction on the first side? Why we are doing the reaction? Because you want a product. You want a product. You don't want a reactant. Okay. You don't take the milk, put in a container, put a sugar, tea powder into it. You want to get a tea out of it, right? You don't want a milk back. You will not waste your gas for that just because you want a milk back. That is like a nonsense, right? We want to perform reaction because we want to get optimum amount of product in a minimum time, in a minimum expense. Okay. And that is why Le Chatelier, he was a scientist. He worked on so many chemical reactions. Out of them was Haber's process, where ammonia formation was there. Ammonia formed from the reaction of nitrogen gas with the hydrogen gas, where so many different catalysts were tried, a different number of conditions of temperature and pressure were tried, and finally they reached to a conclusion. That conclusion he gave to the whole world, and that helped us to obtain as much amount of product as we want in a minimum expenses and a minimum amount of time. So it is really like what I would say, it's really it's like a boon. It's like a boon for a chemist. Okay, chalo. Let's see what this principle says. According to this principle, if a system at equilibrium is subjected to a change of concentration, pressure, or a temperature. According to this, if a system at equilibrium is subjected to a change of concentration, pressure, or temperature, the equilibrium is shifted in a such a way so as to nullify the effect of change. It's like you must have played seesaw, right? You must have played a seesaw in a garden. So in a seesaw, this is the balancing side. You got two sides. One side is at the top, other side is at the below. So how does this Le Chatelier principle works? If you try to press this side downwards, what does equilibrium tries to do? So you are pushing this down. That means this must be going up. So when this is going up, system try to bring it down so as to nullify the effect by which you pull this down. Okay. In other words, see, if you increase the temperature, system will try to go in that direction where temperature is decreasing. Or if you increase the concentration, system will try to decrease that increased concentration which was done by you. Okay, we will see it one by one. Okay, for the time being, Le Chatelier principle says that if a system is in equilibrium and if it is subjected to change of concentration, pressure, or temperature, equilibrium shifts in such a way so as to nullify the change which was done by you. Okay, let's see the first thing, the change in concentration. The change in concentration. See, if an equilibrium, if you increase the concentration of a reactant, results in a shifting the equilibrium in a favor of products. Let me tell you how this actually works. What they are saying, if you increase the concentration of a reactant, you get the more and more product. Why? Because if you increase the concentration of reactant, that means you have brought a change in a concentration of reactant. So the system wants to go to its original state. So what would system do? Whatever amount of reactant that you have increased, system will try to decrease it. And how it can decrease it? It can only decrease it if it converts that increased amount of reactant into product. That is what it does. And that is why in that process, whenever you are increasing the amount of reactant, the amount of product also increases. Let's put this in a different way. Okay. Let's take suppose A reacting with B to give you C plus D. Okay, let's put it in a very simple way. I'm putting it in a very simple way now. Suppose initially you have a 10 moles of A, 10 moles of B. Okay, when the reaction was proceeding, it formed 5 moles of C and 5 moles of D, and then equilibrium was achieved. Okay, so according to our equation of equilibrium, what must be its Kc? Kc is 5 into 5, 25. 25 divided by 100. It is equal to 0.25. 0.25. Okay. Now it is 0.25. Kc, we are calling it as equilibrium constant, right? So it's a constant. That means it should remain constant. Its value does not changes. Even if you increase the concentration of a reactant, even if you decrease you do whatever you want, the value of Kc will not change. We are calling it equilibrium constant. So constant, that means it means something, right? Now this is your regular equation. Okay. Suppose what I do is that I increase the concentration of A and B by factor of 100. That means I increase the concentration of A 10 times and increase the concentration of B also 10 times. Now your Kc is equal to, we don't know how much product is. Suppose we are having a same amount of C and D. So let's consider it as x square. And you have 100 into 100 at the bottom, right? 100 into 100 is how much? 10,000. So your x square is how much? We know the value of Kc, right? Kc is equal to x square upon 10,000. What is Kc? Kc is 0.25. So you have a 0.25 here. 0.25 into 10,000 is equal to your x square. And therefore, x square is equal to, if you count this, how much is become? 2500. It becomes 2500, right? By taking the square root of 2500, how much it becomes? It becomes 50. It becomes how much? 50. So you can clearly see here, when I increase the concentration of A and B, how much C and D you got now? Now you got C and D as 50. Initially it was how much? Initially it was 5 moles. Now how much it is? 50 moles. That means amount of product that you formed is increased. Okay. But remember, mark my words and listen to me carefully and observe also carefully. Kc hasn't changed. Kc is just the same in both the reactions. Initially also it was 0.25. Now also it is 0.25. That is why, and that is how, when you increase the concentration of reactant, to balance the Kc or to maintain the value of Kc, what does equilibrium do? Is that equilibrium increase the concentration of product also. That is why, when on increasing the concentration of reactant, concentration of product also increases. What if I do this in a reverse way? If I decrease the concentration of reactant, then what will happen? If you decrease the concentration of a reactant, now amount of product will still have a constant. Kc is also constant. So if you are decrease the concentration of a reactant, that means system tries to go in a reverse direction so as to compensate for the loss of concentration of a reactant. That means if you decrease the concentration of a reactant, reaction will go in a reverse direction. If you increase the concentration of reactant, reaction will go in a forward direction. This is for reactant. Now let's talk about the product. Suppose A plus B reacts to give you C plus D, And as soon as C plus D forms, if you remove it from the system, suppose C plus D are liquid or gases and you have attached a tap to it, okay? As soon as C plus D forms, you just remove it. Then which direction will the reaction go? In that case also, reaction will try to go in forward direction. Why? Because you have removed a C plus D by yourself. So system will try to refill that. And in that attempt to trying to refill it, system will go in a forward direction, making more and more product. Okay. So you will think that's all okay. We will do what? As soon as product forms, we will remove it. Every time we will remove it and product will keep on forming. No, that will not form, that will not happen for forever. That will not happen for forever. You cannot fool the reacting system for forever. You can fool it for some time, okay? And as soon as the reacting system realizes it, it adjusts itself to attain the new equilibrium constant. So whatever value of product you kept on the right hand side, system will try to react only that much of reactant so as to maintain the value of Kc. And therefore, after some time, even if you remove the product, reaction will not go as such to the product side. Okay. So that is what it is. So that is for decreasing the concentration of product. Then what will happen if I increase the concentration of product? Obviously, reaction will try to go in a reverse direction in favor of reactant. Because if you increase the concentration of a product, reaction system will try to do what? It will try to decrease the concentration of a product. And in that case, it will try to go in a reverse direction. That is how Le-Chatelier principle works, especially when you are changing the concentration. Okay, so moving ahead. Change of pressure. See, this change of pressure is a really tricky thing. It's really tricky thing. Let me tell you why. First, let's write what I have actually put there. When the pressure on a system is increased, when the pressure on a system is increased, the volume decreases proportionately. And we know that from our knowledge of Boyle's law. We know that from our knowledge of Boyle's law that P is inversely proportional to volume, right? So when you increase the pressure on the system, the volume will decrease proportionately. As the volume decreases, the total number of moles per unit volume increases, right? Because what is the formula for concentration? Concentration is N by V. Concentration is N by V, number of moles per unit volume. So when you are increasing the pressure, the volume will surely decrease. When this volume is decreasing, the total number of moles per unit volume appears to be more. So when total number of moles are appearing to be more, system will try to go in that direction where number of moles are less. Whatever you do, it is just like Newton's third law of motion, equal and opposite force of reaction. It is just like that. Whatever you do, system will try to do the exact reverse in an order to nullify the change that you made. Okay, so let me explain it once again. When you increase the pressure, we know that when you are increasing the pressure, the volume will decrease. When volume is decreasing, the concentration, which means number of moles per unit volume, that will increase. When that increase, system will try to go in that direction where number of moles are decreasing. And that is why when you increase the pressure, according to Le-Chatelier principle, the equilibrium shifts in the direction in which there is a decrease in number of moles. Okay, I hope you must have got this. Then if there is no change, this is when number of moles of reactant and product are different. Okay, suppose if there is no change in number of moles of gases in a reaction, that means number of moles of reactant and number of moles of product are same. In that case, no matter how much pressure you increase, no matter how much pressure you decrease, it will not affect that particular reaction at all. Why? Because even if you increase the pressure now, volume will decrease for sure. Then the number of moles per unit volume would be more, that's for sure. Then reaction will try to go where the number of moles are less. But reaction realizes that there is no side where total number of moles are either more or less. They are just the same. And that is why the case where total number of moles of reactants and products are same, in that case, pressure change does not affect the equilibrium. Okay. I hope you must have got it and enjoyed it also. You will enjoy it furthermore when I cover the question based on this. Okay. Chalo. Moving ahead. Change in temperature. See, as your knowledge of reaction, you must have understood there are two types of reaction. One is exothermic, another is endothermic. So suppose A plus B, it is reacting to give you C plus D. And suppose delta H is negative for this reaction. Now delta H is negative, that means what? This reaction is exothermic. And exothermic means what? This reaction is releasing heat when it proceeds to the product side. Now suppose if you try to increase the temperature of this reaction. Now remember one more thing. When the forward reaction is exothermic, the backward reaction has to be endothermic. Which is obvious. If the forward reaction is exothermic, if the forward reaction is releasing suppose 100 kilojoule per mole of energy, then the backward reaction will absorb same amount of energy. In other words, whatever exo or endo the forward reaction is, backward has to be exactly opposite of it. And we know that exothermic reaction releases the amount of heat or energy, whereas endothermic reaction absorbs the amount of energy. That is why if the forward reaction is exothermic and if you try to increase the temperature of the system, then reaction will go in the reverse direction. Why? Because when reaction is already releasing the heat and you are providing it heat to it further, so reaction will obviously detects it that you are providing the heat to it, and reaction will think, okay, if you are providing a heat, then I will try to go in that direction where heat is needed to be absorbed. And heat is needed to be absorbed in endothermic process. And endothermic processes happens to be reverse in this case. And that is why whenever, let's consider it in a simply way, whenever you increase the temperature of a system, the system will try to go in an endothermic direction. If you try to decrease the amount of heat, then reaction will try to go in an exothermic way. Because when you are trying to decrease the temperature of a system, that means the overall heat of the system is decreasing. So overall heat of the system is decreasing, that means system will try to heat it more. And if it tries to heat more, that means it has to go in a exothermic way. And that is why if the temperature, if the temperature at equilibrium is increased, reaction will proceed in the direction in which heat can be used. And heat can be used only in a endothermic way, right? Thus, increase in temperature will favor the forward reaction for endothermic reaction. Forget about this forward and backward. That you can always find out when a given numerical, uh, you can always find that from a given numerical. You just need to understand if the temperature is increased, endothermic reaction will happen. If the temperature is decreased, exothermic reaction will happen. And I also told you the reason for it. Okay, you just don't need to mark these things up. You need to understand it how they are happening. Okay. Similarly, increase in temperature will favor the backward reaction in a exothermic reactions. Here I have just summed it up for you to get it. Okay, but you can always apply the logic to it. So moving ahead, I hope you have understand you must have understood it thoroughly. If you have any doubt, you can ask me in the comment section. Okay. Hello, I'm waiting. You can ask me if you want. Okay. So moving ahead. Now, free energy change. What is free energy change? See, free energy change gives you spontaneity of a reaction. It gives you spontaneity of a reaction. If the given reaction, if the given reaction is spontaneous, its delta G has to be negative. Delta G has to be negative. So what is the formula? The delta G, the delta G is equal to delta GO plus 2.303 RT log of Q, where Q is what? Q is a reaction quotient. What is reaction quotient? Reaction quotient and Kc are just the same thing. Reaction quotient and Kc are just the same thing. Okay. Only difference is that Kc is also equal to Q. But when equilibrium is achieved, when equilibrium is not achieved, that Kc is nothing but a Q. Okay. So delta G is a delta G0 plus 2.303 RT log of Q. At equilibrium, delta G is how much? Delta G is 0. If delta G is 0, this value becomes 0. Then delta G, sorry, this value becomes 0. Then delta G, O, that is standard free energy change. That O stands for standard free energy change. Then that delta G O is equal to minus 2.303 RT log of K, where K is what? Your K is equilibrium constant. Okay. If your delta GO is negative, that means reaction is spontaneous. If delta G is positive, reaction is non-spontaneous. If delta G is 0, then reaction is at equilibrium. Okay, sure. Moving ahead. Concentration quotient condition. Concentration quotient condition or a reaction quotient. See, for a reaction AA plus BB gives you XX plus YY. See, at any other stage of the equilibrium, the expression Q is equal to X raised to X, Y raised to Y divided by A raised to A, B raised to B. That is what your Q is all about. Okay, so your Q is concentration quotient or a reaction quotient. Okay, so for the reaction AA plus BB gives you XX plus YY. So at any other stage, at any other than the stage of equilibrium, that means if you have attained the stage of equilibrium, then Q is nothing but your K only. That means your reaction is in equilibrium that time. But if the value of Q is less than K, then obviously if the value of Q is less than K, reaction will try to go in a forward direction. Why? Because it wants to make Q equal to K. That is why when Q is less than K, the reaction will tend to increase till it becomes equal to K. And that is why, and that is how the reaction will go in a forward direction. Okay. If the Q is higher than K, if the Q is higher than K, that means you need to decrease the K. Sorry, you need to decrease the Q for it to be make equal to K. And for it to make equal to K, it need to go in a backward direction. That is why when value of Q is higher than K, reaction goes in backward direction. When it is smaller than K, reaction goes in forward direction. And if both of them are happen to be same, that means reaction is in equilibrium. Okay, I hope you must have enjoyed it. You can like and comment. You can also subscribe to our channel Practically Live on YouTube. Okay, so moving ahead, let's solve this numerical now. In the reaction, PCl5 is giving us PCl3 plus Cl2. Let's write this reaction here. It is the reversible reaction, by the way, but I just put single symbol here. PCl3 pi is giving you PCl3 plus Cl2. Okay, now what they're saying, degree of dissociation is 30%. That means 30% reaction has been proceeded. If the 30% reaction has been proceeded, suppose if we have started with the 1 mole of PCl5, The 30% has happened. That means PCl5 must have been dissociated to give 0.30% PCl3, 0.30% Cl2. Sorry, let me write it in a different way. Initially, when you start, okay, let's put it in a different way. Initially, when you start, moles of PCl5 are 1, PCl3 are 0 and 0. Okay, that is initially. Then the degree of dissociation is how much? 30%. So that means PCl3 is 0.30, Cl2 is also 0.30. So 0.30 has been dissociated. So how much PCl5 must have remained? 1 minus 0.30, and that is equal to how much? 0.70. So this is at equilibrium. This is at equilibrium. And what they're saying, if initial number of moles of PCl5 is 1, then total number of moles at equilibrium is how much? So total moles at equilibrium is equal to 0.70 plus 0.30 plus 0.30. 0.70 plus 0.30 is 1. 1 plus 0.30, 1.3. That is why our answer has to be A. That is 1.3. That is how you can use or you can solve this kind of numerical. Okay. Moving ahead. For a reaction, HI gives you half moles of H2 plus half moles of I2. The value of Kc is 1 by 8. Then what is the value of Kc for exactly reverse direction? Let's write all of them. Let's write the Kc first. For the first reaction, Kc, let's write this as Kc1. Let's write this as Kc2. Okay, so as to make it easier. For a first reaction, Kc1 has to be H2 raised to 1 by 2, I2 raised to 1 by 2 divided by Hi. Okay, and this is equal to Kc1, which is also equal to 1 by 8. Equation number 1. Okay, equation number 2. If you look at the Kc2, look at this Kc2. Kc2, you have a Hi on the product side, Hi square, right? Then you have concentration of H2, concentration of I2. So if you look at the relationship between Kc1 and Kc2, you can clearly see if you reverse the Kc1 and square it. If you reverse the Kc1 and square it, you will get the Kc2. That in other words, your Kc2 is equal to 1 by Kc1 square. You can see that clearly. See, Kc1, you got Hi at the denominator. Kc2, you got Hi at the numerator. And this is Hi, this is Hi square. This is H2 under root, this is H2 normal. That means if you square the Kc1 and reverse it, you will get the Kc2. And that is why putting the value of Kc1, what is the value of Kc1? 1 is equal to 1 by 8 square. In other words, 8 square. 8 square is how much? 64. And that is why, and that is how your answer is B, that is 64. Okay, I hope you must have understood it and enjoyed it also. If you have any doubt, you can ask me in the comment section. Okay, I can wait for you for a minute, then we can move ahead. Yeah, anyone? Okay, chalo, moving ahead. In an equilibrium, H2 reacts with I2 to give 2Hi. Again, this is also reverse direction reaction. Okay, it's a we are in a chapter of equilibrium, so every reaction has to have a reverse direction also. Okay, so in equilibrium reaction, H2 reacts with I2 to give you 2Hi. the delta H is minus 300 calories. That means H2 reacting with I2 to give you 2HI. This forward reaction is exothermic. Okay. So what they're asking, which factor favors dissociation of HI? That means they are talking about the reverse direction here. You're getting my point. If you look at the forward reaction is not a dissociation. In forward reaction, H2 plus I2 is reacting to give you HI. And reverse direction is dissociation of HI to give you H2 plus I2. That means one more thing. The forward reaction they have already told us is releasing 3000 calories. That means forward reaction is exothermic. And backward reaction has to be endothermic. And what is the backward reaction? Dissociation. And that is what about they have asked us only. So which factor will then favor dissociation of HI? It has to have a high temperature, because reverse direction is endothermic and endothermic reaction is accompanied by absorption of energy. And when can you absorb the energy? When you are providing it. And that is why it is the high temperature only. Okay. So next question. The next question, N2 reacting with hydrogen to give you, this is in gaseous phase. This is also in a gaseous phase. Both of them are reacting like this to give you 2 moles of ammonia, which is also in a gaseous phase. Okay. Now, if temperature of following equilibrium reaction, increases, then what happens? See, for ammonia, there are some reactions for which you need to remember the condition. And now, not all the reactions for which you need to remember. There are very few reactions. It is one of those few reactions. Why? It's because this reaction holds the importance of so many other reactions. This is a historical reaction, and that is why I'm letting you remember that this reaction is having delta H negative. That means this reaction is exothermic reactions. And since it is exothermic reaction, obviously, if you increase the temperature, reaction will try to go in a reverse direction. That means if the temperature of the following equilibrium reaction increases, then equilibrium will shift to the left hand side. Okay, because reaction is exothermic. Chalo, moving ahead. Next, at 298 Kelvin, the equilibrium constant K1 and K2 of the following reaction. That means for reaction number 1, this is your K1. For reaction number 2, this is your K2. What is the relationship between K1 and K2? Let's write the K1 for first reaction first. K1 is equal to SO3 divided by concentration of SO2 and O2 raised to 1 by 2. Or you can say AO2 under root. That's your K1. Okay. Obviously, equation number 1 that. Then you have K2. K2, you are having SO2 on the product side. So SO2 square. Then you got O2. And then you got SO3 square. So if you want to obtain K2 from K1, what you need to do? You need to reverse the K1 first, and then you also need to square it. See, if you reverse and square it, what do you get? SO2 square, O2 under root raised to 2, that means normal O2 divided by SO3 square. That means the relationship between K1 and K2 is your K2 is equal to 1 by K1 square. K2 is equal to 1 by K1 square, which makes your answer K2 1 by K1 square. Yeah, that means your answer is C. Got it? Let me tell you once more. First, you write the K1. K1 is what? SO3 divided by SO2, O2 under root. Then you wrote the K2. For the K2, SO2 square, O2 divided by SO3 square. So when you observe the relationship between K1 and K2, you can see that if you square the K1, then also you will not get K2, but you need to square it. But along with square, you also need to inverse it. When you inverse and square the K1, you will get the K2, or it's the other way around. When you inverse the K2 and take the square root of it, you can get the K1. See, you can also write it in this way. K1 is equal to 1 by under root K2. So it is that way also. And that you can obtain from this relation also. Okay. In exam, they can give you any relation. They can give you this relation also. They can give you this relation also. But that's a normal mathematics. And I hope everyone must be aware with that much of mathematics. Okay. So moving ahead. Next. Some gaseous equilibrium are given. Okay. The one is K, K2 and K1 and K2. And they have asked us to find out the relationship between this equilibrium constant. See, such a kind of questions been asked so many times in exam. Such a kind of questions are been asked so many times in question exam. Okay. So let's write one by one. Let's write the first K. K is equal to CO2 into H2 divided by CO and H2. That is our equation number 1. Then K1. K1 is what? K1 is CO2 square divided by CO square and O2. And lastly, you got the K2. This is equation number 2. K2 is what? K2 is H2O square divided by H2 square and O2. That is your equation number 3. So equation 1, 2 and 3. Now we need to find out the relationship between them. So firstly, they have said first relation is K1 into K2. If you multiply K1 into K2, do we get the K or not? We need to observe that. So if you multiply this equation and this equation, let's see what do we get. If you multiply this and this, then nothing is getting cancelled out and you are not getting K also. So that means this cannot be your answer. Secondly, K is equal to K1 into K2 bracket square. K1 into K2 bracket square. So are we getting then also? Let's see, K1 into K2 bracket. No, then we are surely not getting. I think it is K1 by K2 and then square. But anyways, so for here also we are not getting it. Then we got C, K1 by K2 rest to 1 by 2. Rest to 1 by 2, that means what? So suppose K1 into K2. So K1 you write like this, CO2 square. See, you are multiplying, you are dividing K1 by K2 and then taking under root. Then taking under root, that means this CO2 becomes what? This, you are taking square root of CO2, no? So it becomes normal CO2. Then you got a CO multiplied by O2 rest to 1 by 2, no? You are taking a square root multiplied by, now this will become reverse because you are dividing K2, no? You can look at the option number C. Okay. So you are dividing K2, that means H2 and O2 will go up. So taking square root, H2 will stay as it is. O2 rest to 1 by 2. Taking the square root of H2, that means H2. Okay. So you can see here, this O2 raised to 1 by 2, O2 raised to 1 by 2 gets cancelled. And what we are remained with is this CO2 H2 divided by CO and H2. And this equation is equal to K. You can see here. This is a K. This is also K. That means your K has to be K1 divided by K2 under root 1 by 2. That is why your answer has to be C. Your answer has to be C. Okay. That is how you can find out the relationship between different equilibrium constant and you can find the correlation between them. Okay. So moving ahead. For equilibrium process, x plus y gives you xy. If the concentration of x and y is doubled, then the equilibrium constant becomes twice, becomes half, unchanged, become thrice. You know what's the answer, right? It is unchanged. I told you earlier, even if you increase the concentration of x and y, you will get more and more product which is xy. So that means as if you take the equation of equilibrium constant, the product is in the denominator, reactant is in the numerator. So as soon as you increase the value of numerator, let me write it here. Your Kc is equal to concentration of xy divided by concentration of x and concentration of y. So as soon as you increase the concentration of this numerator, you twice state the concentration of xy also increases. So that Kc remains constant. So doesn't matter. Even if you increase the concentration of x, if you decrease the concentration of x and y, if you increase the concentration of xy, or even if you decrease it, the equilibrium constant always remains unchanged. It remains unchanged only. Remember that always. Next, 2 moles of PCl5 were heated in a closed vessel of 2-liter capacity. At equilibrium, 40% of PCl5 was dissociated into PCl3 and Cl2. The value of equilibrium constant is. How can we solve this? This PCl5 question you will see appearing in so many times and so many questions. Okay? Because it is one of the most celebrated reaction. So PCl5 is dissociating. Reaction is the reverse, obviously, to give us PCl3 plus Cl2. Now, firstly, we write initially, remember, then at equilibrium, right? Now, initially, you need to understand or find out how many moles of PCl5 are there. So, there are concentration of PCl5 is C is equal to N by V. How many moles of PCl5 are there? 2. What is the volume? 2 liters. So 2 by 2 is equal to 1. That means you have a 1 mole of PCl5 only. So therefore, you got a 1 initially, 0 and 0. Now what they're saying? At equilibrium, 40% of PCl5 was dissociated. Now 40% is dissociated. That means you are getting 40% of PCl3, 40% of Cl2. And how much PCl5 is remained? 1 minus 0.40. That means how much? 0.60. Right? Then what is the value of our Kc? Kc is equal to PCl3 into Cl2 divided by PCl5, which makes it 0.4T into 0.4T divided by 0.60. Now you can always solve it like this way. Kc is 40 into 10 raised to minus 2. Or let's make it 4 only. 4 into 10 raised to minus 1 into 4 into 10 raised to minus 1 divided by 60 into 10 raised to minus 2. So your Kc is equal to 4 into 4, 16 into 10 raised to minus 2 divided by 60 into 10 raised to minus 2. 10 raised to minus 2, 10 raised to minus 2 gets cancelled. You got Kc is equal to 16 by 60. So 0, 16 twos are 120. Then you got 4, 0, 0. 16 6 are 360. Again you got 4, 0, 0, 16 6. So you basically get Kc is equal to 0.266. By using significant figure, it becomes 0.267. And that is why our answer here is 0.267. Okay, that means answer is A. That's how you can solve the numerical of such kind. Okay, if you have any doubt, you can ask me in the comment section. Okay, so moving ahead. Next, consider the following reaction in equilibrium with equilibrium concentration 0.01 of every species. What they're asking, what is the extent of the reaction taking place? Now they're saying whatever number of species you are having on either side of all these three reactions, every species is having the concentration 0.01. Then we need to find out the value of Kc. The reaction having higher value of Kc will be having more extent of being taken place. Okay, so let's find out Kc for first reaction. For this reaction, PCl3 into Cl2 divided by PCl5, right? So how does it, the value of Kc becomes 0.01 into 0.01 divided by 0.01. 0.01 gets cancelled, another remains. So 0.01, which is equal to 1 into 10 raised to minus 2. That's the Kc for first reaction, right? Now, second reaction. For second reaction, H2 into I2 divided by Hi square. That means 0.01 into 0.01 divided by 0.01 square. And at the numerator also you have 0.01 square, right? So 0.01 square divided by 0.01 square cancels, you get value 1. Now you can clearly see here the Kc2 is higher than Kc1. Why? Because Kc2 is 1 and Kc1 is 1 into 10 raised to minus 2, which is 0.01, which is definitely smaller than 1, right? So till here you must have got this. Now the last part. Last part again same. How do we find out the Kc for this? On the numerator side you have 0.01 square, right? On the product side you got 0.01 into 0.01 cube, which makes Kc3 is equal to 0.01 square divided by 0.01 square into 0.01 square. And we can always do this because this makes 0.01 raised to 4. So square gets cancelled. Your Kc3 is equal to 1 divided by 1 into 10 raised to minus 2 square, which makes your Kc3 is equal to 1 divided by 1 into 10 raised to minus 4. Therefore, Kc3 is equal to, this goes to the numerator, 1 into 10 raised to plus 4. That makes this to be equal to 10,000. Your Kc3 is how much? Kc3 is 10,000. 1 into 10 raised to 4. That is why the third reaction is fastest here. Then, the extent of third reaction being taken place is more than the second. Second is having more extent than the first, which makes the correct option being your B. 3, 2, 1. And that is why our answer here is B. Okay. I hope you must have understood it and enjoyed it also. Chalo, moving ahead. Next, for the following gases, equilibrium N2O4G is giving us 2NO2. Following gases, equilibrium N2O4 is giving us 2NO2. Kp is found to be equal to Kc. Kp is found to be equal to Kc. This is attained when? This is attained when? Now, firstly, write what is the Kp and Kc relationship here. As we all know, Kp is equal to Kc RT raised to delta Ng. And what is delta Ng? Delta Ng is number of moles of product minus number of moles of reactant. Number of moles of product are 2. Number of moles of reactant is 1. So 2 minus 1 is equal to 1. So therefore Kp is equal to Kc RT raised to 1, which makes Kp is equal to KCRT. Kp is equal to KCRT. Now what they are saying at what temperature Kp is equal to Kc. Now Kp can only be equal to Kc when RT, this product of R and T is 1. You're getting my point? Kp is equal to Kc into RT, right? If your product, which is RT, if it becomes 1, then Kp naturally becomes equal to Kc. Okay. So your R and T, we need to find if it becomes 1 or not. Now value of your R here is 0.0821. Okay. So that is constant here. Let's take different temperatures, find that out. The first is 0.0 degrees Celsius. 0 degrees Celsius and 273 Kelvin. Both of them are one and the same thing, because you need to take temperature in Kelvin only. So even if they have given you 0.0, even if they have given you 0 degrees Celsius, you need to take it as 273 Kelvin only. Okay. So that means these both options are one and the same thing. It will obviously save our time. So let's take 273 into R. R is what? 0.0821 multiplied by 273 degree Kelvin. Okay. So your 0.0821, let's make it 8.21 into 10 raised to minus 2 multiplied by 273. So 8.21, let's take a 8 only so that it will help our calculation. 273 into 8. 8 3s are what? 24. 4 2. 8 7s are 56 plus 2 58. You got 8. 5. 8 2s are 16. 16 plus 5 21. 2184. Decimal points are moving to 21.84. So the product is 21.84, which is surely not equal to 1. That means A and B both cannot make Kp equal to Kc. Third option, K. Third option is 1 Kelvin. Now 1 Kelvin means what? 1 Kelvin. So 1 Kelvin, that means value is 1. So if you multiply 0.0821 by 1, it becomes 0.0821 only, which is surely not equal to 1, right? So that will not make Kp is equal to Kc. That means that option also goes. So in the exam, ideally, if you don't get A, B, C as right answers, that means answer has to be D. Okay. But here I'm going to tell you how. So 12.19, that's your D. Then we need to take 8 RT. No, we need to find out RT. R is 0.0821 as we have taken already. Multiplying by 12.19. Okay. So again we are taking 0.081. Instead of that we are taking 8 into 10 raised to minus 2 into 12.19. So 12.19 into 8. 8 9s are 2, 7. 8 1s are 8 plus 7, 5. Then you got 1. 8 2s are 16 plus 1, 17, 1. 8 1s are 8 plus 9. 9752, 2 decimal, 97.52. So 97.52, that makes you can make it almost equal to 100 into 10 raised to minus 2. That means it is nearly equal to 1. Actually, it has to be larger than 97.52. It will go somewhere closer to 100. Why I'm saying this? Because it was 8.21. I ignored that 8.21. So if you take that 8.21, it will surely become 100. That means in this case, your RT is becoming 1. When your RT is becoming 1, it has to be making Kp equal to Kc. Okay, that is how you can solve this kind of numerical. Okay, moving ahead. For the gas phase reaction, C2H4 reacts with H2 to give you C2H6. C2H4 plus H2 reacts with C2H6. Delta H minus 32.7 kilocalorie. Delta H minus 32.7 kilocalorie carried out in a closed vessel. Carried out in a closed vessel. The equilibrium moles of C2H4 can be increased by. Read it carefully what they're saying. It is a gas phase reaction where C2H4, which is your alkene, reacting with hydrogen to give you alkane. It is that is C2H6 in a closed vessel. The equilibrium moles of C2H4, that means they are asking the reverse direction. They are asking the reverse direction. They are asking C2H4. You can see here the equilibrium moles of C2H4 can be increased by. So if you look at the forward reaction is exo, but they are asking us the reverse direction. So reverse direction has to be endo. So how can we increase the concentration of C2H4 reaction being an endothermic? Obviously by increasing the temperature. That's for sure, right? Because the reaction is endothermic, and endothermic reactions can be achieved by increasing the temperature. That is for sure. Then removing some H2. If you remove some H2, reaction will try to compensate forming more H2. And forming more H2, in that process, more and more C2H4 will be formed. That means that is also the case. So removing some H2 will also help. A can make this happen. C can make this happen. Now, decreasing the pressure, will that help or not? See, when you increase the pressure, reaction will try to go in that direction where number of moles are less. That is when you increase the pressure. That means when you decrease the pressure, reaction will try to go in that direction where number of moles are increasing. And number of moles are increasing here in a reverse direction. That is why decreasing the pressure will also help achieving our target. And lastly, adding some C2H6. Obviously, this has to help. If you add more C2H6, reaction will try to make it less. And in an attempt to make it less, it has to go in a backward direction. In other words, all these four options can make us achieve increased moles of C2H4. Okay, that is how we can solve this kind of questions which are based on Le-Chatelier principle also. Okay, chalo, moving ahead. This C reacting with H2O to give us H2G plus CO. By increasing the pressure following equilibrium, what will happen by increasing the pressure? See, this reaction, the number of moles are less on the left hand side of gas, and this is a solid state concentration. If you remember, the concentration of pure solids and concentration of pure liquids are taken to be unity. That means their concentration is 1. You can simply ignore them. So basically we need to look at the concentration of this only. So we know that when you increase the pressure, reaction will try to go in that direction where number of moles are decreasing. So here, when you increase the pressure, you can see reaction will try to go in a reverse direction. A reverse direction, because in reverse direction, number of moles are decreasing. That means this reaction will proceed in a backward direction. Okay. So moving ahead. Next, in the following, PCl5 gives you PCl3 plus Cl2. In the following reaction, PCl5 gives you PCl3 plus Cl2. at constant temperature rate. At constant temperature, rate of backward reaction is increased by. If you keep the temperature constant here, out of these four factors, which factor will increase the rate of a backward reaction? Backward reaction is what? Backward reaction is PCl3 combining with Cl2 to give us PCl5. Okay. So the very first option they have given is inert gas. Inert gas mixed at constant volume. So let me tell you this point. This point was actually coming into the discussion of a Le-Chatelier principle. See, if you are mixing inert gas, mixing of inert gas at constant volume doesn't affect anything. It doesn't affect. Remember this. If you are keeping the volume constant, so even if you increase the concentration of inert gas or even if you mix the inert gas into it, how does it matter? You remember when we increased the pressure, the volume was decreasing. Volume wasn't constant in that case. So when you increase the pressure, volume was decreasing and total number of moles per unit volume was increasing. So to balance that, reaction was going in that direction where number of moles were less. And that is why it was affecting there. But if you keep the volume constant, nothing will matter at all. So that is why option A cannot make this happen, because this reaction, when you are going from product to reactant, number of moles are decreasing. Cl2 gas again mixed at constant volume. This will also not affect. So third, inert gas mixed at constant pressure. Yes. See, when you mix an inert gas at constant pressure, now pressure is constant. Now pressure is constant, but volume is not. So when you add inert gas to the system, what will happen? Pressure is constant, but volume will increase or decrease. So if you mix the inert gas now, the total number of moles of gases are what? They are increasing. If you mix the inert gas at constant pressure now, so pressure is constant. So that means if you increase the number of inert gas in that system, the total number of moles will increase. If total number of moles are increasing, system will try to go in that direction where number of moles are decreasing. And number of moles are decreasing in a reverse direction here. And that is what we want here. That means rate of backward reaction is increased by C, not also D. Why? Because again D you are having the system at constant volume. As I told you, constant volume, if you are having a constant volume, inert gas mixing or mixing of any other gas will not affect. You need to keep the pressure constant but not the volume constant. Okay, so moving ahead, I hope you must have enjoyed this. Now the ionic equilibrium. Now that we have started chemical equilibrium chapter, we have almost covered every part of chemical equilibrium, solving every numerical possible, and in that it almost took 1 hour and 10 minutes. So we are remain only with the 20 minutes for us to cover the ionic equilibrium. Okay, so we will try to cover as much as possible today. Okay, even if some part remains today, as I told you, totally we have 20 sessions. Okay, but we will try to finish it off in 18 or 19 session. So we will take one extra session for the ionic equilibrium numericals then, because it is important. It is as important as chemical equilibrium only. Okay, but that will be the case when we won't be able to finish any of the ionic equilibrium. We will try to finish as much as possible today and now. Okay, but I won't rush it, because if I rush it, there is no point in making it. Okay, because you need to make it. I need to make you understand it in a better way. So, a strong electrolyte. See, there are two types of electrolyte. What is mean by electrolyte? It is a substance which dissociates in a given solvent. It is a substance which dissociates almost completely in a given solvent. Now, not every substance dissociate completely. Some substances dissociate completely. We call them strong electrolyte. Some substances dissociate partially or to small extent. We call them weak electrolyte. So, strong electrolyte is defined as a substance which dissociate almost completely into its ions in aqueous solution. Okay, and hence they are very good conductor of electricity. Now, what are strong electrolyte? All these strong acids are strong electrolytes. Strong acid means the acids which dissociates or acids which releases H plus ion immediately are termed as a strong acids. All the strong bases, all the strong acids you can see here, H2SO4, HCl, these are strong acids. All the strong bases, NaOH, KOH, these are all strong bases. All the types of salt, all the types of salt, all of them are what? Strong electrolyte. Okay, then what is weak electrolyte? Weak electrolyte is a substance which dissociates to a small extent in aqueous solution and hence they conduct the electricity to a small extent, which is obvious. If they are dissociating to a less extent, they will produce less ions. Less ions means less electricity. Okay. So what are weak electrolytes? The weak electrolytes are weak acids. Wa means weak acids. Weak bases, that means Wb. So weak base, that is NH4OH, it's a weak base. And weak acid, that is acetic acid. Apart from that, there are some other acids also. For example, HCl. HCl is a weak acid. It is also weak electrolyte. Okay. Then you have a CuOH2. It's also weak base and a weak electrolyte. Okay. Next. Degree of dissociation. What is mean by degree of dissociation? See, it is the fraction. It is the fraction of total amount of electrolyte which dissociate into ions is called degree of dissociation. So basically degree of dissociation is denoted by symbol alpha. Alpha is equal to fraction of total amount of electrolyte dissociated into ions. In other words, alpha is equal to total amount of electrolyte dissociated divided by total amount of electrolyte taken. Total amount of electrolyte taken. That is called as alpha. So it is the fraction of electrolyte which has been dissociated. Okay. You obviously multiply it by 100 to making it the percentage degree of dissociation. Okay. Chalo, moving ahead. Now, there are some concepts of acids and bases which are really helpful for you to solve the question based on them. Okay. So there are three theories: Arrhenius, Lorentz, and Lewis. I'm just summing them up in a shortcut. Okay. According to Arrhenius, the concepts of acid base, he says that a substance which gives H plus ion in aqueous solution. Aqueous solution means what? A water solution. So any substance which gives H plus ion in an aqueous solution or in a water solution is an acid, or any substance which releases OH minus ions in aqueous solution will be termed as a base. For example, HCl, if you put HCl into water, it would release H plus ion plus Cl minus. So that means HCl is an acid. HNO3, H2SO4, HClO4, then you have what? H3PO4. All of them on reaction with water does release H plus ion plus their corresponding conjugate base. For example, in HNO3 it's NO3 1 minus, in a sulfuric acid is HSO4 1 minus, in HClO4 it's a ClO4 1 minus, and in H3PO4 it's H2PO4 1 minus. But that's a different thing. So all of them are Lewis acids. And what are bases? NaOH. If you dissociate NaOH into water, it would give us Na plus plus OH minus. KOH with water also release K plus and OH minus. So any compound that release hydroxyl ion in a water has to be termed as a base. But there was a flaw in this system. What was that flaw? That Arrhenius has only considered compound as acids and bases in an aqueous solution only. That means what if I change the solvent from water to alcohol, water to ammonia, then would that compound which was releasing H plus ion in water, would it release H plus ion or not? Then or even if it releases, can we call it as an acid or not? So that was a thing. Secondly, what about the compound which does not release H plus ion? Like there are n number of compounds which do not release H plus ion at all. Still they are acids. What about them? So RNAs do not had any expression for that. Okay, that was why it was rejected. But still it is useful to find out whether given compound is acid or not or base. It is still helpful. Okay, so next theory came, that is Laurie Bronsted concepts of acids and bases. What does it says? It says an acid is a substance which can give or which can donate a proton, and base is a substance which can accept a proton irrespective of its medium and irrespective of its solvent, and state also. That means you can take any solvent that you want. You can take water, alcohol, ammonia, acetone, benzene, ether. Take any solvent that you want. Take any phase, solid phase, liquid phase, gas phase. If your compound is donating a proton, it's an acid. If it is accepting a proton, it has to be a base. It was that straightforward, and it is one of the most celebrated theory of acids and bases. Okay, but then this theory also had some flaws. What was those flaws? Again, this theory do not consider a compound which do not release H plus ion. Again, that flaw remained there. Then that flaw was removed and corrected by another scientist whose name was Lewis. What does he say? He said an acid is a substance which can accept a lone pair of electron. So any substance which can accept a lone pair of electron would be termed as an acid, or any substance which donates a lone pair of electron is a base. So bases are basically lone pair donors and acids are lone pair acceptors. For example, what are the Lewis acids? BF3, BCl3, BBr3, then you got BI3, FeCl3, sorry, AlCl3, AlBr3, all of these are Lewis acids. Because in all of these compounds, their octet is incomplete, they can accept a lone pair of electrons. Base. Any compound which is having a lone pair, any compound which is having a lone pair is termed as or is classified as a Lewis base. For example, ammonia is having a one lone pair. Then you got the water where you got a two lone pair. Then you got the alcohol, oxygen is having two lone pair. Then you got the amines, all of them are having lone pairs. So all of this compound or any compound which is having a lone pair can be termed as a Lewis base. These are some of the terms of acids and bases. These theories are really important. Okay, so moving ahead, my job here is to only summarize it. Okay, I cannot make every concept. I cannot teach you every concept here. Okay, because you know that we are in the crash course. Remember, we have exam scheduled on 12th of September. That is why practically has brought an exclusive course of a NEET crash course for you. Okay. Sure. Next is ionic product of water. Now, ionic product of water, KW, is what? How does water dissociates? water dissociates. If you take a water and if I write its dissociation on a classical way, we would write it as H plus plus OH minus. That's a classical way. Then your Kw is how much? So then your dissociation constant, just write K only. K is equal to H plus, concentration of H plus, concentration of OH minus, divided by concentration of H2. Now water dissociates to a very small extent. Water dissociates to a very small extent, which makes concentration of H2O practically constant. It is practically constant. So K into H2O is equal to H plus plus OH minus. So therefore K into H2O is termed as a new term, which is Kw, and therefore Kw is equal to H plus plus OH minus. Now H plus doesn't exist actually as such. H plus actually exists like this, H3O 1 plus. So basically you can write the dissociation of water as H2O plus H2O. H2O plus H2O, they are giving you H3O 1 plus plus OH minus. So that is why you had a H3O plus plus OH minus here. So this product Kw is called as ionic product of water because it is the product of ions of water. Okay, and that product is equal to H plus concentration is 10 raised to minus 7, and for OH minus you are having concentration of 10 raised to minus 7. So the product becomes 1 into 10 raised to minus 14. Okay, that is at 25 degrees Celsius. That means at 298 degree Kelvin. And remember, if you increase the temperature, this value of 10 raised to minus 14 will surely change, because on increasing the temperature, water will dissociate more and more, and then you will have more concentration of H plus and OH minus. That is why on increasing the temperature, the ionic product of water changes. pH is equal to minus log of H3O plus, or you can also call pH is equal to minus log of H plus. We can always say that. We know this definition, we had learned them as a child. POH is equal to minus log of OH minus. Okay, pKa is equal to minus log of Ka. pKb is equal to minus log of Kb. We all know that, right? Kw is equal to H plus plus OH minus. We had seen that 10 raised to minus 14. So if you take the logarithm, if you take the negative logarithm of this equation, the negative logarithm of Kw becomes, or make it pKw, which makes it pH plus POH. Now pH is 7, POH is also 7. Therefore pKw is always equal to 14. It is always equal to 14. That is how these terms are. These terms will come handy to you when you are solving the numerical based on that. Okay, moving ahead. See, pH of an acidic buffer. You might know what buffer is. Buffer are the substance which resist the change in a pH. Buffer are the substance which resist the change in pH when small amount of acid or base added to them. When small amount of acid or base added to them. So what is the formula for acidic buffer? There are two types of buffer: acidic buffer, basic buffer. What is acidic buffer? Acidic buffer is the equimolar mixture. It's the equimolar mixture of a weak acid and its salt with a strong base. For example, a weak acid like acetic acid plus its salt. That means weak acid salts with a strong base. So you can take acetic acid as a weak acid. You can try to combine it with a strong base, which is NaOH. This is Sb strong base. This is weak acid Wa. So CH3COH plus NaOH. NaOH will give you OH minus. CH3CO minus will give you H plus. So OH minus plus H plus will give you water. Water goes out and what will remain is CH3CO minus Na plus. This is a salt of weak acid and strong base. So that is how the mixture of acetic acid and CH3CONA is called as acidic buffer. So acidic buffer is a equimolar. That means amount of concentration of acetic acid plus concentration of sodium acetate, which is this salt, is exactly same. So it's equimolar mixture of weak acid and it's a salt with a strong base. That is what called as acidic buffer. What is its formula? The pH is equal to pKa plus log of concentration of a salt divided by its conjugate base, or you can say acid. That's the pH formula for acidic buffer. Then basic buffer. How do you find the basic buffer again? It's a equimolar mixture of a weak acid and it's a salt with a strong acid. The weak base is NH4OH. Now NH4OH is a weak base and it's salt with a strong acid. That means strong acid, suppose if I take HCl. So NH4OH plus HCl, this OH plus this H plus ice goes out in the form of water, and what we have is NH4Cl. So basically equimolar mixture of NH4OH and NH4Cl. This mixture is called as basic buffer. What is the formula for basic buffer? How can we find out its pH? Firstly, it's the basic buffer. That is why you can find out pOH only. pOH is equal to same formula as it was for acidic buffer, pKb. Here it was pKa because that was acid. This is base, so it's pKb plus log of concentration of salt divided by base. Because it is base, in earlier case it was acid. So this will give you pOH. How can you find the pH then? We know that pH plus pOH is equal to 14. So pOH, you can find out the pH 14 minus pH. You know that already, right? That is how the acidic and basic buffers are. Okay, so moving ahead. Yeah, now we can hardly solve these two numericals today because we are about to end the session now. But as I have promised you, we will cover the remaining chapter or remaining questions of ionic equilibrium in once we finishes the other chapters completely in almost 17 or 18 session. So which of the following is most soluble in water? See, this is the solubility product constant. Now, what is the formula for solubility? How can we find it? Suppose we have a MNS. What suppose we already have a MNS there? It gives you Mn2 plus and S2 minus. So 1 mole of this, suppose gives you 1 mole of this and 1 mole of this. Then how can we find out the KSP? The value for KSP is this 1 as to 1, then this 1 as to 1 plus S raised to 1 plus 1. That is our formula. So 1, 1, 1 remains 1. S 1 plus 1, it remains S square. So if you so the system or the compound which is having the highest value of S would be most soluble in water here. So S square, what is the value of 8 into 10 raised to minus 37? So if you take the under root of S, S will become somewhere around 10 raised to minus 18. Right? If you take this is also S square. You can see here Z and S will dissociate as Zn plus 2 plus S2 minus. Again 1 S2 1, 1 S2 1, S raised to 1 plus 1. So again S square is equal to 7 into 10 raised to minus 16. So under root 7, you know, it will become something like 2 point something. Okay, 2 point something, whatever it is, 2.2, let's suppose. 10 raised to minus 16 under root 10 raised to minus 8. That is your S. So 10 raised to minus 8, 10 raised to minus 18. Next, Bi2S3. Bi2S3 will dissociate as 2Bi plus 3S2 minus. 2Bi 3 plus. So this is 2 raised to 2, 3 raised to 3, S raised to 2 plus 3. 2 raised to 2 is 4, right? 3 raised to 3 is how much? 27. So 27 into 4, 108. So it is 108 S raised to 5. So S raised to 5 108 s raised to 5 for 10 raised to minus 72. So if you find its s, it is somewhere around 2.3, somewhere around 10 raised to minus 2.3. Okay, you can find that. Lastly, Ag3PO4. Ag3PO4 will give you 3Ag plus PO4 3 minus. So 3 raised to 3, 1 raised to 1, s raised to 3 plus 1. So 3 raised to 3 is 27. 27 s raised to 4. So s raised to 4 is 1.8 into 10 raised to minus 8, which makes s is equal to 10 raised to minus 2. And 10 raised to minus 2 is larger than 10 raised to minus 2.3, which makes the highest value of S of silver phosphate, making it most soluble in water. Okay. And lastly, addition of HCl will not suppress the ionization of. See, this is the question of common ion effect. And according to common ion effect, the the dissociation of a weak acid, the dissociation of a weak acid gets suppressed by addition of a strong acid having an ion common with it. Common with it. Now acetic acid gives H plus ion, benzoic acid gives H plus ion, H2S also gives H plus ion, and HCl also gives H plus ion. But HCl is a strong acid than all of these three. So that means it will suppress their ionization. But it will not suppress the ionization of sulfuric acid. Why? Because sulfuric acid is a stronger acid than HCl. It will dissociate already to more extent. Actually, it's either way around. Sulfuric acid can suppress the ionization of HCl, but HCl cannot. Okay, so that's it for today. We have already gone past our time. Okay, but no problem with that. Next lecture, not next lecture actually. In the upcoming session, as soon as we finishes the whole syllabus for NEET crash course, I will cover the other part of ionic equilibrium. Okay, but for the time being, you can like, comment, and subscribe to Practically channel on YouTube. Okay, we have interesting courses like Vedic maths, robotic, chess for you. Okay, we are bringing this more interesting courses for you, and we have an app called Practically on a Play Store, and it is also on a Google Play. You can download it from there, you can rate us there, you can log into it, and you can explore more and more interesting things there. You would really love it, I promise. Okay, so that's it for today. Bye bye from my side. Let's meet tomorrow from the next session.